Sorry.
No problem. In Hakata University, and today I will give a talk about multimodal AI for intelligent robotics. So basically, I'm not a robotics guy. I'm a multimedia guy. But from last year, I'm very much interested in robotics. So I do something on robotics human interactions. So about my experience, from 2021, I come to Japan in 2021, and I become a project researcher is kind of a postdoc in the University of Tokyo Yamasaki lab. And in 2023 October, I was promoted to an assistant professor, and then in 2025 April, I joined Hokkaido University as a tenured associate professor, and from 2025 August to now, I am a visiting researcher at the University of Tokyo. My research interests are multimodal AI, machine learning, and now I do something on robotics AI.
Sorry for interruption. Can you reshare your screen, because it's now I can see just presentation mode.
Sure. I'll go now.
Let's see. Okay, great.
Yeah. Sure. Oh.
It's not moving.
Yes.
Oh,
yeah,
it moved. Okay.
Yeah. So my research basically is mostly about multimodal AI. So for example, for image test, I'm not sure whether you're familiar with this task. It's about for example, we take fishing as an example. I do something like this is about how you calculate the. Can you see? No. This is about you calculate. For example, you have several items like the tops, the bottom skirt, and t-shirt and shoes, and we calculate how much attractive, how much finishing if you combine them together, if you wear them together. This is about finishing compatibility. We care about how can we combine, how can we wear different clothes together and to make you look fashion, or for a specific situation like a business class, how can you choose your suits. And also the fill in the blank is like you already have this cast, and now you're considering what kind of skirt you should wear, and our model can recommend something that is more suitable or more compatible with your current outfits. So this is kind of our image test, because we have some test attribute of the image items, and you also have some image, and then we try to calculate their compatibility and similarity. So compatibility is like they are not similar, but they look compatible to each other. And similarity is just, you only care about the similarity, like a texture similarity, pattern similarity. That's it. I will go very quick about that, because I guess you might not interested in that. Yes. And I also do something video test. It's like, for example, you have a very long video, and we care about, but you do not have enough time to watch all the video. It's because it's very much time consuming, and you only want to watch some contents that you are interested. So you can input some the test, like conversations and interactions between characters. Like I only care about the conversation parts, and then our model can generate the extracted short videos that only contains the conversation parts from the original long video. For example, if you say that I only care about the background, the scenario, and the landscape, and our model can extract the frames that are related to the background. And I also do something on video generation. And for example, this is open source. I guess many of you are familiar with that. If you do AI, it's kind of a sort of model in video generation. And so, for example, if you give the 3 prompts, a single white flower gradually blooms from a single green flower bud, And from 2, the single white flower is blooming. And from 3, a lovely, fully bloomed single white flower. And the open source can give you like this. So this is kind of a text to video generation. You just need to input the text, the 3 sentences, and then it can generate this video. And this is, we have not published this paper yet. This is where we're still doing experiment on that. This is our generated one. So it's more consistent, like compared to the current open source. This is also one topic we are currently working on. I also do something on more modalities, not only image test or video test, because these modalities are very familiar with everyone. We are also interested in work on some modalities like the gender of the user and the age of the user and the locations of the user. This kind of attribute that is, we call it heterogeneous modalities. And so this is the paper that we got a best paper award in ICMR last year. So this is a model based on vision language model, and we designed several this is the main novelty comes here, the task adaptive knowledge. We try to develop different kinds of retrieval augmented generation strategies and to make it customized to different tasks. And as you can see, this is a unified model, and we can address 6 tasks at the same time. So first, like the landmark recognition and image captioning. Landmark recognition is you input an image, and the model can generate the recognition of the landmark name, the tourist spot name, like it's Ginza Onsen. Onsen, I guess you know, hot spring. So, and for image caption, it's like you give an input as an image, and the model can generate a description text of this image. So this caption like the spot is closer to hot spring, and please explain the content in this image, and our model can generate, oh, it's green and has a strong sulfur smell. And also we do, the model can do like a general review generation. So like, please generate a review from society. For example, you travel somewhere, you book some hotel, you visit some tourist spots, but you do not have time, or you don't want to spend time to write a review of the tourist spots you are visiting. And our model can generate an automatic review for you, like browser was beautiful, I enjoyed eating while feeling the history. Also, image caption without the sport name, without the sport name. For example, it's green, green and has a strong sulfur smell. And also conditional review generation, like you're a female tourist. For example, if you want to customize your generated review because you have some preferred tones that you want to write these comments, and we can, like, you can input as a prompt. You're a female tourist with family, please generate a review of sensor like cherry blossom blooming. I enjoy working with my family. So we can also do tourism recommendation. For example, you with the sensory sky tree, and you have a 1-day trip, and you care about how much money you spend on the traveling, and how much tourist spot you want to visit within today, and where you want to start, where you want to end, and we can generate a tourist plan for you. And I have a demo later, so I can show you that. So basically, this is a unified model that it can address more modalities larger than 10 and 6 tasks at the same time. So it's a collaborative decision-making kind of things. And the main novelties comes here. We design many kinds of image-based retriever, summary retriever, text to image retriever, image text retriever, text expansion, different kinds of retrieval augmented strategies to achieve, to satisfy different tasks. And this is our demo system. So we do not do any acceleration in this demo system. So you say you can choose the hotel that you stayed, and the hotel you want to arrive, like, and you have detailed condition like the number of viewpoints, like how many tourist spots you want to visit today, and the popularity. Did you care about the popularity, or you care about more about the distance, or you care about care more about the number of recommended routes, and also detailed condition like which season you're visiting and the day of week, like which day is Sunday or is weekdays, and also the user attributes, you're a man or woman, or you're with your family, or you're traveling alone. So you can set different attributes, different conditions that you require, and our model can generate recommended routes very quick for you. And also you can modify if you are not satisfied with the recommended routes.
Is currently Osaka. Where the city is?
Himeji is one city here. Himeji.
Okay.
And you can see the recommended routes automatically on the Google Maps. Actually, you can if you put your mouse here, you can also generate the review comments automatically. But this part is a little bit slower, so we didn't put it in this demo system.
What is the language model backbone?
Lava.
If you're using other backbone, then it works better.
I think so, because currently Xiao model is very strong. So if you try Xiao model, you might can get even better performance. But when we submit that, Xiao model is not, yeah.
What's the hardware you're using?
With GPU, NVIDIA A100.
And have you actually tested the survey after user uses your model, then actually do the tour, then satisfactory? How much they like the suggested route by the model?
Sorry, can you repeat?
So if I use this model and I get some kind of places where to visit based on this model,
Yeah.
and if I do actual like a tour
Yes.
on my own, and then kind of do survey how much I like.
Yeah, the user experience.
Yeah, did you have that?
No, we didn't do that.
Okay.
It's hard. It takes it's hard for example, it needs some users to really experience that.
Yeah.
Go from there to there and to see whether they're we are now welcoming any commercial collaborations, but not yet. Yeah.
Okay. Maybe if you're a visitor in your university, maybe I then use this model and then do the tour in
Yes.
Sapporo, I guess.
Yes. And I also do something on machine learning because this is very much because we work on multimodal things, but machine learning is a basis, and we still need to keep updated in machine learning. So, for example, we do something open setter recognition, and if you call it open world model in robotics, you might be very familiar with that word. So it's like you have some in distribution data, and you want to detect something that your trained model have never seen it before, and also this is out of domain of your original trained data set. This kind of task. I also do something on this, and also on continuous learning. I also have one student work on continuous learning combined with VLM and robotics right now. So this is about, like, for example, I guess you might be familiar, interested in that. For example, in robotic setting, the robotics work operate outside. It will collect data always collect have new data generated, right? But if the robot see new things, it's almost impossible for you to always try to retrain your whole AI models. So continuous learning is like you don't need to retrain, always keep retrain, updating your whole model, but you can use some small data from the new phenomenon, new environment to update your model and to keep good performance on the new scenario. And also, you do not forget the knowledge about the older environment, the previously gained knowledge. So this is the continuous learning setting. And we also have some publication here. This is the publication when I was assistant professor in the University of Tokyo. So finally, why I'm here? Basically, I'm a multimedia researcher who is very much interested in robotics. I am to do some interdisciplinary research in this area. So last year, since I built my own lab, I started to do some research on robotics AI. So today I will give you some brief introduction of my the research from my lab this year. Basically, not only half year, because I joined Hokkaido University in 2025 April, but I cannot have my own student from April because they cannot announce that I will be there. So the first round for me to get my student is from October last year. So until now, basically only half year. But we still have some research to report. This is a video generated by. First, I want to claim that this is directly driven by via vision foundation models. And for all of you, you might think that vision foundation models, it might be hard to deploy because it have high latency. How can we deploy via a large scale vision foundation models on small robotics and expect it to work real time? So it's almost impossible for all of you to assume. Some people think that it's almost impossible, and you might consider that we just need some lightweight transformer structure to do an end-to-end motion planner, and this might be very quick. But I have to say that VLM is also possible, and this is driven by Chairman 3VL 4 billion models. So let me show this video. So it can, now we use RGBD sensor, and it can detect there is people who are chatting, or there are some obstacle that I should avoid to move forward anymore. So currently we can achieve this, and but this is of course it's still not good enough because the current scenario is kind of simple. It's not not so many people, not very crowded, and it's not like a real scenario, but at least VLM is possible on this task. So what do we do this year? First, let me give you some brief recap of the existing works. So this task is about building vision foundation models for social robotics, for social robot navigations. And for related works, we see some paper for example, VLM social nav. This is one paper that it's directly use ChatGPT. At that moment, it still use ChatGPT 4V, and you might know that ChatGPT 5 is already available currently. So they use ChatGPT 4V to do environmental perception, and the environment the ChatGPT 4V will output some test instructions, like to give some instructions of a current environment, and then they combine this with their other modalities input, like RGB image, 3D radar, auditory Google pores and combine them together, do a scoring module, and to generate an end-to-end deployable navigation model. The problem is that if you directly call the key from the current vision foundation models, basically you cannot use GPU acceleration. So it's very, very much slow. And if you cannot use GPU acceleration and you use that kind of large scale vision foundation models, basically it's almost impossible for you to deploy it end to end. So I guess in that paper they might first generate some well-defined environment and then combine them together, use them directly. This is the only thing that I can assume that they can they can deploy it very quick. I mean, generate their actions very quick. And also, we found that non-trainable LLMs struggle to understand complex social norms. Basically, not only social norms, but also spatial information. This is also one current very big disadvantage of current VLMs. They are struggling to understand some spatial information. The reason is that currently all the VLMs, they are trained with some data, some open source data, but the open source data, most of them are 2D. And so this means that you basically do not have any 3D spatial information from the currently open source data. So it's no way for the current VLMs to gain some spatial awareness from the current open source VLM models. And some models, they try to fine tune it. For example, they fine tune a larva model with the RGB input, image input, and language instructions. They fine tune a model to generate some tester instructions, high-level tester instructions in navigation. But the problem is fine-tuned large language models also have high inference latency. And I only write one up here, but actually there's another one bigger disadvantage is that for current task, we do not have very large scale social navigation data set. And so if you train a very large models on a very small data, there's one phenomenon you will see, like your model will still have memory from a previously pre-trained task. So this means that you can generate some reasonable output, but if you make the model to work continuously, you will see that the model accurately will generate some knowledge from the previous task. So this is not what you want if you want to deploy this system. And so the motivations for our research is that we want to build efficient vision language models for socially compliant robot navigation. So for large VLM, it has better accuracy and large latency, and small VLM is low accuracy and low latency. So this is what we call scaling load in VLM. But according to this scaling law and currently the common knowledge of vision foundation models, so we consider that if we focus on smaller VLM, basically we have low latency, but we need to focus more on how to enhance the accuracy of the vision language models. So this is basically the current point that we are focusing on right now. First work is we propose e-social llama, which is accepted to ICASS 2026 this year. This is a collaborative work with Xiao from George Mason University. What we do is that we fine-tune small language models. Okay, first I give you a common knowledge about what is small language models. So for small language models, we do not have a very consistent definition of what kind of model is small. Some people also say 7 billion is small, but among all the definitions, a definition that is widely accepted that if the language model size is smaller than 3 billion, we think that it is small language models. Of course, some people also call 4B, 7B is also small, but it depends, So in our paper, we think that if the model is smaller than 3 billion, it is small language models. So we train the small language models, but the problem is, as we said, you use the small language models, so basically you cannot assume your model have very high perception and decision-making ability. So what we do is that we also corrected a direct performance optimization (DPO) dataset and try to fine-tune the pre-trained model with reinforcement learning, and we also call it IOHF, reinforcement learning with human feedback. So the DPU dataset is the DPU dataset will provide the human feedback to the model training. So how do we correct the DPU datasets? For example, we have a human input, like what should the robot do, and the choosing the original controls, like the robot should stop, wait for a clear path, and then we will correct another rejected one, like the robot should continue straight. So we build this kind of choose and rejected answers to mimic the human feedback in training the model. And if you see the right-hand image, you see the human mind asks what should the robot do, and the choosing the robot should continue straight at a moderate speed, and the rejected one mind, the robot should stop and wait. So in this case, we created some direct performance optimization dataset to optimize the model performance. And as you can see that after using DPO, it improves a lot in the bird. Okay, let me introduce what is a bird score. A bird score is token level perception accuracy, and expert score is a sentence level. So if we talk about language model, you have token level and sentence level, and SMS of course is also semantic calculation. And you will see that after using DPO, it improves the token level and sentence level perceptions. And the FPS is kind of not that large; it's still 2 point something. But I have to say that it's also scattered, because it all depends on the current status of the GPU. For example, if A100 using one A100, and if your model status is good, it can also over 3 FPS something. But sometimes if the GPU is very slow, and it 2 point something is also makes sense. So this is just a round value. And here we show some visualization result that our model generated. For example, if the user output what did you perceive from the image, and the instruction level is our model. It can generate something like the robot is moving forward on a sidewalk with a very slow crowd density. There's one human, a person wearing a black hat, moving from the northwest to the southwest at a slow speed. And the ground truth is there's a human on the left side of the sidewalk moving from the northwest to the southwest at a far distance. And also, for example, if you ask what this human will do next, our model might predict that the human will walking from the northwest to the southwest and continue moving at a moderate distance. And the ground truth also the same. And what should the robot do? And our model can help the robot should continue moving forward at a moderate speed. And the ground truth can be the robot should continue moving forward at a moderate speed. So basically, we do not expect that a model can be very correct, but basically it has some sense of social navigation knowledge after training using our proposed method. But we also find some failures. For example, in the left image, the ground truth can be the robot should turn left at a slow speed, but our model might output the robot should stop. And in the right hand, the ground truth can be slightly turned to the left, and our can be that continue move forward at a moderate speed and keeping a slightly turning radius. So basically, you cannot say the model predicted result is totally wrong. So after analyzing the failure cases, we found that there is an ambiguity in social navigation. So in many cases, you might do not only have one correct answer. So and based on these findings, we also do some research on this part, and I will introduce later. But before that, we also find another problems. We train our ICASP paper model on SNET dataset, but we find that for SNET data, they have some self-contradiction. For example, this is one example from their dataset. For prediction, for reasoning, they say, oh, since the robot is directed ahead and moving straight ahead, the robot should stop intermediately. But the action can be go straight at a normal speed. So they have some, self-contradictions in the multi-dialogue conversations. this is basically toxic information for training the model. So so by finding their self-contradiction, limited actions, and a small size, and we corrected our Multimodal data set. This paper now is on archive, and when it's on archive, we only propose 800, but now we have extended it to 10,000, and we will release next month maybe. And but anyway, let me introduce how do we correct this data set. So first, we since this task basically it is a high level, it's not a low level. I mean, direct motion play. So we think that we do not need that detailed, directions, and so we roughly divided the directions into 6, like move forward left, move forward right, turn left, turn right, and stop. And for the five round dialogue, and we try to keep it consistent, all the dialogue, and to remove all the self-contradiction within all the labeled samples. And specifically, we include very diverse scenes, 6 urban environment and variable density, and the action designs discrete space balanced distribution, and structured annotation, 5-step champ sort quality control, and several application task evaluation. So for diverse scenes, it consists of indoor like libraries, shopping malls. For outdoor, it consists of parks, streets, plazas, and campus. And we also have a variable crowd density, like space from empty parks to highly crowded mall. And for action design, we design discrete action spaces aligned with beyond token generation. It mapped continuous navigation into 6 semantic actions. And we also solve the long tail bias, try to keep move forward to obey physical inertia and ensure geometric symmetry to avoid directional bias. And we also have structural annotation, 5-step jump sort, perception, prediction, reasoning, action, explanation, ensure the decision is explainable and socially compliant. Also, quality control, we use a 3-step labeling phase. The AI system pipeline ensures logical consistent step 1 human annotation, step 2 AI check, and step 3 expert review. The application task is that it can be applied to social perception, like can the model identify dynamic agents and static obstacles. And task 2, socially compliant planning, can the model choose the correct step action. Task 3, socially aligned COT reasoning, can the model generate the full 5-step jump sort process. And task 4, explanation generation, can the model explain its decision in natural language. So, but anyway, we have expanded this dataset to 10,000 now. I think it's good enough for training some small-scale vision learning models. So we will update our archive version very soon, maybe next month. So if you are interested, and you can try our dataset, and we will release the dataset link as well in the paper. So then we also, as I introduced before, like there is social ambiguity. For example, in this image, what should the robot do? If the ground should give that the robot should turn left at a slow speed, but basically the robot should stop, it's also a reasonable choice, right? Or the robot should turn right. It depends. For example, we say in Japan, turn left. And we in US or in China, it might turn right. It's also a good choice. So it depends. So we also have some work on how to solve the social ambiguity, and this paper is currently on the second round review of our journal submission. So what do we do with that? We design an action social net model, try to generate several possible actions from one scenario. For example, we first created a multimodal data that have several possible actions, and we design a mental cognitive prompt MCP for promoting the VLM to be more intelligent, to generate multiple possible actions. And this is a data set that we created. For example, we also created a 3-runner chunks or annotations. And what do you perceive, 5 John, what do you perceive and what do you notice they are doing together? And what is the prediction and other elements? And finally, the only thing different from most things that we labeling not only one plausible actions, but several. We list all the possible actions, but we do not control how many actions you have. For example, for some samples, you might only have one action. For example, in that case, only one is possible. But for some sample, we have 2, we have 3. For example, in the left image, we label 2, move forward and move forward right. And in the right image, we label 3, like stop, move forward and turn left. So it depends. And this is the overall model structure. First, we have a multimodal input, the image, and a test. Test consists of perception, prediction, action. And the system prompt we design is meta-cognitive self-evaluation and competitive stimulated reasoning. And they are inputted into a NVIDIA structure, which is our baseline model. And we fine-tune both the vision transformer encoder, the predictor of the vision encoder, and the LLM. And finally, our model will output the ranking of all the possible actions, and from the from the high priority to the low priority. So this is details of the designer prompt. For MCSE, the prompt is like you implement a silent recursive self-evaluation loop. Before answering internally generate a draft and score it based on strict safety and social adherence standards, and set a 90 score at the minimal % but do not cap the score at 100. If our solution is safety robust or you are highly confident, you are encouraged to assign a score exceeding 100. If the score is below 19, you must critically analyze the flaws, refine logic, and stimulate the outcome again. Repeat this internal iteration until the solution meets or exceeds the 90 point. Therefore, output only the final optimized response without reviewing the intermediate thinking steps. So this is the MCSE. For CSR, like you are intelligent assistant specialized in social compliance and urban navigation, you must understand human behaviors, infer intelligence, and plan safe, smooth, and socially appropriate paths. You should perform competitively against humans, other AI models like you. So this is the design system prompt, and this is the result we obtain. We compare with GPT-4 Cloud. Both are the latest version where we submit our paper. If you see that our model, but one thing I want to point out that for Cloud COT, our model achieved the comparable performance. But for others, ours is much good. But this is not the thing I want to show. One thing I want to show is here. And we find that for the current the solar vision foundation models, they will generate, if you ask them to generate a candidate list, they tend to generate a lot. For example, this is the average pre-read number of ChatGPT-4 with Cloud, ChatGPT-4 with Champsort, and ChatGPT-4 with root. And these are different prompts we designed, some overrun, and we try to explore all the potentials of the current state-of-the-art vision foundation models. And we found that, for example, we only have 6 candidates in the dataset, but GPT-4 raw will generate almost 4, and 4, 5, almost 3, and almost 4. But for ours, we will generate a constrained answer. Like we do not need to, the average of our generated candidates is 1.5. So I have to say that if you see the previous predictor something, this is highly affected by how many candidates you generate. For example, if you already generated all the candidates, all the 6 actions, you will get a very high prediction accuracy. But this is not what we want, because you generated all of them, and this is equal to nothing. Because no suggestion at all, no useful information at all. But ours, we will generate a constrained number of the candidates. So this means that our model really knows in which case it should stop, generate, and in which case it should generate some candidate list. Here we show some realizations. For example, if you see the ChatGPT-4 and Cloud, you see they always tend to generate a lot of actions. like the 3, 4, 5 something. And but for ours, if for example in this case only 1 is allowed, and our cases with the proposed MCP it will only generate 1, but without MCP sometimes it generates 2. But anyway, it will not like GPT-4 and cloud generate a lot of candidates. And we also found that our model is much more effective in the difficult situations. So for difficult situations, if you compare with if you compare this without MCP and with MCP in difficult situations, it improves a lot in their prediction accuracy. And here it also shows some more realization like GPT-4 and cloud. You see, they always tend to generate a lot of candidates. Even though, for example, in the left side image, the ground truth is only have 1 answer move forward, but GPT-4 will generate 6 of their actions, and the cloud generates 3. And in the right hand, the ground truth is 2 actions move forward and turn right, but GPT-4 will generate 3, and the cloud generates 6. So so this means that they basically do not know. They just they do not know social knowledge. They just randomly generate their answers. And this is our another work about it. We propose a competitive learning (GCL) global competitive learning strategy to better balance accuracy and efficiency. And this is similar to node distillation, but not node distillation. And let me recap the node distillation. And you might know that node distillation is a very effective strategy if you want to, for example, in design efficient models, or you try to further enhance the model representation learning. But the problem is for traditional distillation, they are affected by the model capacity. So this is another kind of a common knowledge in node distillation if you do that. But our design strategy, we do not care about whether your model is trained well or not, and whether your model have the similar structure, and whether your model have different capacity or the same capacity. We care nothing, and you just use our method, and you can use it for any models, and it can improve your performance. And this paper is also in revision now. So what do we do that, for example, you have a test input and evaluation input, and you have 2 different models. I have to say that these 2 models you can change to any model. And we also even do not require your model is fine-tuned well or not. We don't care about that. And even your model is good or not, high, very large or very small, all different structure, TMV and lava, we don't care about that. And in many cases, we have tested that until now, all the cases, our model, our strategy can improve the performance of both of them. And so what we do is that we design 2, the main knowledge is 2 parts, the group competitive strategy and asymmetric learning optimization. For group competitive objective, for example, you have 2 models, model A and model B. And for traditional supervised fine-tuning state, you will have auto-regressive loss. This is like a prediction nest token. You might know that if you have some knowledge about language models. And what we do is that we extract the hidden feature embeddings from the model A and model B, and we calculate their feature distance. And finally, you will also generate a logic distribution, the vocabulary distribution, and we also calculate the attribute distribution using the Gaussian divergence laws. And finally, so basically we design these 2 laws, the constructive laws and JS divergence laws, and combine them together as a total loss. And we found that it's very much effective in enhanced model. And also for asymmetric graph optimization, you have model A and model B. And as I said, in node distillation, normally you have a teacher model and student model. But in our case, we don't care about which is teacher model and which is student model. And you don't need to define it, because our strategy can define it automatically. It will automatically define which one has high capacity, which one is higher performs, and that one will be guide, and another one will be learner. And for the guide, we have low learning rate. For the learner, we have high learning rate. And for the learning model, we also have low temperature, and the small model, we have high temperature. This temperature is a hyperparameter in notification function, KO diversity loss. So this is kind of important hyperparameter. So, but anyway, we set this kind of rules to optimize the model performance. And this is some result. We will update this archive paper soon as well, maybe also next month, because we do experiment. We further enhance the model, and we do experiment on some large scale data set. And if you can see, for GCL is the proposed method. So no matter the baseline situation, the baseline model, and the GCL, when you use GCL, you can always enhance the model performance. And we don't care about who is learner, who is guide. And for example, if you change the learner guide in the up and in the lower, and you don't see any degradation in the model performance. Of course, our current model is more advanced, but anyway, we will update it latest version next month maybe, or July. It depends because it takes some time to finish the experiment. And if you see here, there are some evaluation studies. For the SFT, we do experiment on status and multi data set, and we got this kind of performance. And you use GCL, and you will see some improvement in the model performance. And I have to say it's much better than the previous. And especially if you consider you train your model on this kind of small scale data set. Here we show some realizations. For example, in the left side, you see the ground truth is turned right to yield and continue moving northeast. And the Turing 2.5 models is mind output continuous straight at a moderate speed. And Turing 3 turn right, and Turing 2.5 GCL is our method, like turn right to yield and continue moving northeast. And the right side as well, you will see that our model can with the GCL model. No matter the previous model, what kind of prediction it have, for example, Turing 2.5, Turing 3, no matter, of course they are wrong, but with our model, it can give with our study, it can give a correct prediction. So currently, we work on VRM plus robotics on AI to human learning, reinforcement learning with human feedback, and we also work on DPO is one thing, but now we work more on policy. Reinforcement learning. DPO is kind of off policy because you need to credit the data set. But credit data set is always not the optimal choice because it's very time consuming. So we now working more on policy reinforcement learning, and we also work on efficient VRM design. And I didn't introduce it here because that work have not been on COP. And we also work on ambiguous decision making and continual adaptation. And we might release paper as well. But not yet. And also synthetic data. I also have students work on this. Like, for example, in some scenarios, it's hard for you to obtain the real world data. And how can you use current generation AI to create some data that can make your model we call it a noisy data or dirty data. But if you use them wisely, you can still have good performance. Yeah, that's all, I guess, pretty much. And this is my website, our lab's website, and we will keep updating some papers on this topic. And this year, our lab, we also get a very large budget on the similar topic. So I guess we will actively working on this topic as well, at least in the next 5 years, because that project support us for 5 years. So if you're interested, and I'm also welcome any research collaborations, of course, from Domin's lab. Yeah, all of you are welcome. Or some student if you want to visit Hokkaido University, and you can talk to your supervisor. Yeah, yes. Thank you very much.
Thank you. Any question from audience?
I just wonder, so I think it seems like the published data, they're mostly based on the lab experiment. Do you have any plan to bring into like a regular people like me and test your system or your model?
You mean recommendation system?
I mean, do you have plan to test your model to regular people like me?
Which model?
I mean, any model like a navigation model for the robot or the tour model?
Yes, we have. And for the work 4, actually, we are now the student after they finish all the experiments on the GPU, and we will conduct some comparison experiments using the robot we have as the video I showed at the beginning. So we will. But for the recommendation system, this is one work I do when I was assistant professor in the University of Tokyo. So I should discuss with the professor, and we mind because we also spend some money on the demo. So we might want to attract some commercial collaborations or sell it to some companies. It depends, but we are welcome. And I am now also closely collaborated with him. So we are also on this topic. So of course it's in our plan, but not yet.
So in that case, the user will interface with your model by text or by voice?
In robotics, in this case, just like this, no text input. Now our model do not have this function. Because the current model we do not take audio as one input. Okay. So currently the model cannot understand audio, but the model can understand the vision, the image.
Only image.
Yes, and video.
Okay. Okay. Thanks.
Yeah, there's a couple of people in Zoom online. I'm sorry to sharing the Zoom link to such a late moment. But if you have a question, please put it in the chat, then I can read your questions. Okay, I have another one question. So you showed a lot of social navigation study.
Yes.
And currently it is more about the data set, right? You're using what kind of data set? I saw the scan. Do you using any other data set?
Currently we corrected the vision language model training data from Mosuhu. They're proposed by Xiao, Mosuhu and Scan.
You're gathering your own data set.
Yes, because for VLM training, currently not so many available data set because it's very hard to label it. And actually, we also have another work. I didn't show it here. Conducted by him, one of my master students. And because we found that the current data set for VLM training, we are missing some egocentric. For example, if you see snake, they have some northwest, southwest. This is bird view, right? But this is basically not what we want. Because all the data are collected from the egocentric view of the human or robot when you collect the data. So now we try to label that. But we found that it's not an easy case if you want to coordinate the 3D information of the human, of everything in your image, in your vision. So my student, him is now trying to solve this problem, and I guess we can relieve in this year a larger scale egocentric vision dataset, and also consider multi-dialogue conversations, because this is one thing that you need if you want to fine-tuning vision language models. Yeah, please go ahead.
Okay. Because based on my understanding, the output of that language model is just turn left or right, or it goes straight. Yes. Is this something you can just synthesize from any navigation data?
Currently, only 6 discrete dataset for Musin. This is just for Musin data. And basically, it can output a test and describe any degree.
No, my question is, because you said that there are not many vision language model, there are not many social navigation data including that language information.
Yes.
Then can you just generate the language from the just normal social navigation data?
We need to currently we found that if you use, for example, the current most powerful model is ChatGPT 5, right? Mm-hmm. And we use ChatGPT and Qianwen, which model? The latest Qianwen model, and we try them to use them to directly generate a language from the vision input. Mm-hmm. And we find that for perception, it's okay. describing the vision from the image is okay, but when you go to decision making, when you go to the action prediction, the human intention prediction, it's very much bad. So we still need human to level it. And now the Muslim data set, I said we extended it to 10,000. We have more than 10 people work on that right now. Just level the data. And this is very slow, for every student, even though they are very much good at, familiar with this task, and normally they can only level 50 every day.
Yeah, but
so it's harder to use, yeah.
But isn't it obvious if you see the sequencer of the image, and then the only thing I need to say is that is it going forward or turning left or turning right? Then it feels like you can actually do that, isn't it? No.
Turn left, turn right. You mean the current model? They can do that?
Yeah, isn't it? No.
No.
No, you cannot.
They cannot. They cannot.
I see.
You will still need a human to level it. It's almost because we already tried the most powerful LLMs. Almost impossible to use the data generated by them.
I see. Okay. No other question?
I was wondering how does it proceed from after the predictions? If the visual language model predicts turn right, then what's the next process? How does it proceed from the prediction to action?
Currently, for example, turn left we can in the deployment we set some distance, like move half meter kind of, and then it will see a new image, and then another prediction.
But isn't that latency issue? Then it will be slow, right?
It's not that much actually, because the model is trained on NVIDIA GPU, and in the inference is much faster. Yeah.
Because there are 3 steps, right? First, even you mentioned chain of thought process, so there are multiple inferences, right?
You mean the chain of thought account for a lot of larger latency, right?
Yeah.
Yes, it's true. But currently, we still can obtain 2 FPS kind of things in the deploy on Jetson. The problem is on Jetson.
Okay.
If you just deploy it on Jetson, do inference, and you don't use the NVIDIA 800 GPU, you can still achieve 2 FPS in our current experiment.
Okay.
And we are now trying to make it faster.
Okay. So this work is primarily for vision language models for navigation. So what are the other comparable models which are not vision language that are already doing well? How is it compared to that?
Sorry, I didn't get you.
The models which are not vision language based, some different any policy based algorithm or.
You mean some lightweight transformer structures?
Yeah, not a language based or just I don't know. I'm not sure about which models exist right now. So I was just wondering how does it compare with, because this feels like it's first perception and then prediction. It's taking much time. Instantaneous the models. I'm not sure about the information, to be honest.
I see. I guess that they are compatible, not directly comparable. Because, for example, this is just a very high-level decision making. Basically, if you want to transform it to the local motion control, you still need another local motion planner, right?
Yeah.
So this is just currently, this is just a high-level decision maker. Of course, there are some VLMs that directly generate the motion, the code generating. It's also possible VLM can do that. But currently, the current structure design, I guess, is more compatible with the local motion planner, not reproducible.
Okay.
But if I interpret, if I try to interpret the question, if this BLM just doing the obstacle avoidance, but in a bit smoother way, and there is already some navigation stacks, all the navigation stacks, something like a detect object, making the obstacle avoidance path, whatever A star or RRT, just classical navigation algorithm. Compared to that, is a BLM doing something special?
Yes. For example, it can generate some explanations.
Okay.
And for example, audio and text, basically they are equal. Just you just need a different encoder. If you can use audio and you can conversation with the robot, and you can alter its actions. So this is the low level end-to-end transform structure cannot do.
I see.
How about if I have just a follow-up question? How about just comparing the performance, such as like the track where you want to go and the time to navigate? Do you see any difference between your model and the previous corresponding models?
You mean compare our model with previous models?
Yeah, like a star or something. In terms of performance, not the interface, but the performance like a...
It's hard to directly compare with A-star because A-star is it's a navigation from start to goal, and we do not have start and goal. We just have you're here. We assume the robot is here, egocentric. The robot, because otherwise this is the reason that robot can. For example, robot is here, and it can only see here, right? We assume the robot is here, and then based on the vision it sees, make a decision what should it move. So it's almost impossible to compare with A-star.
Okay.
I have a question. So is it possible that you also include the global information, like the algorithms that we already have? Like if you know the environment beforehand, can you add to the VLM model to let the robot know what's going on, or is it always depends on the frame that it is currently looking at?
You mean assume the robot already have the knowledge about the environment?
Yeah.
Oh, this is also another thing I want to mention, that why we want to use VLM. Because if you assume you already know that, this is basically not very realistic, right? Yeah. In the realistic operation, you always do not know the environment. Yeah. So this is what VLM can do, but its current transform structure they cannot do.
Yeah, but I'm just saying that if you can incorporate that, if you have a partial information.
Yes.
Into the model somewhat, or is it always a a restriction of VLMs to be only focusing on the current frame?
I see. And then we can set a start point and goal point.
Yeah.
And then we can evaluate the whole planning, right?
Yeah.
Yes, it's correct. And actually, for our workforce, and we will do some experiment like this. Like we assume we will do some experiment in our university, this work, and assume we have the global knowledge of the whole environment, and we set a start point and a goal point, and then we can compare with other methods. Yes, this is what we will do. Otherwise, only based on the current image, it's hard to compare with others. And we can only check the decision-making accuracy, but we cannot check the decision-making in the navigation, whether it's correct, whether it's not, and how much good it looks like. You're right. Yes, we will do that. And I also want to mention that if we include the global knowledge in that, and it's the VLM definitely can generate a much better decision-making because it already know the whole environment. And this is also one thing that if we don't talk about robotics, we only talk about vision foundation models. You talk about RIG, right? For example, you talk about I have a task, new task, and I always want to give the vision foundation models a basic knowledge, a basic definition of this task. So this is similar things. And in robotics, we give the whole environmental knowledge. This is similar to what we give the task definition knowledge to the VLMs when we train the VLM for a task. So I believe it is effective. Yeah.
Okay, great. Thank you very much.
Yeah. Thank you very much.